Hello again, everyone. Welcome to our discussion of section 6.2, where we will be talking about solving systems of three equations with three variables. Now, as you recall in the previous lesson, or the previous video, we talked about solving systems of two linear equations with two unknowns, right? So in this section, the systems that we will be dealing with are mainly larger systems. So we have reached three equations with three unknowns. The method of elimination and substitution that we talked about when we had two equations, two unknowns, will slightly change when we apply it to three equations with three unknowns. So that's one of the two main techniques we will be talking about in this section. The second technique is another technique called the Gaussian elimination, or Gauss-Jordan elimination, or the elementary row operations. All those three names apply to the same technique. But that technique, Gauss-Jordan method, will be different than what we are discussing as method of elimination and substitution. As systems get larger and larger, systems with 4 equations, 4 unknowns, 5 equations, 5 unknowns, and bigger systems, the method of elimination and substitution becomes impractical. So we need a much more useful method, and the Gauss-Jordan method is that method. We will introduce you to that method in this section. So for now, we will begin by reminding ourselves that the method of elimination and substitution changes a bit in this section, simply because we have 3 equations, 3 unknowns. By the way, I hope that, as usual, you have heeded my advice and read through the chapter before you watch the video, and done the note-taking on anything that is important to you, any questions you might have, before you watch this video or before you attend class. Okay, and as usual, please make sure that you complete all the homework for this section by the due date, and please don't forget to spend at least half an hour a week on reviewing the previous material. All right, so now not only that will change, we will also additionally introduce a second very new method. As I mentioned, that method is called elementary row operations, or Gaussian elimination, or also a third name, the Gauss-Jordan method. It's important for me to make sure that you are familiar with these 3 names, because different authors might talk about them with different names, with any of these names, and you should be able to recognize the method as that, as the same method, but with these 3 different names. Okay, no matter which method we use, if we use the method of elimination and substitution, which, by the way, changes a bit, it changes a bit for systems with 3 equations, okay? Or if we use the Gauss-Jordan method, there are certain things that must be the same regardless of which of these methods we're using. And that's that all these variables must be in order, x, y, z. So we can't have z on that side, like I've shown here, as one incorrect format. Or we can't have y first and then z and then x, or y, x, z. All the variables must be on the left side, and they must be in order, just like what I've shown in the correct form for the above equation. Okay, so the above is not correct, it's an incorrect form. This one is the correct form of having our equations set up. And this is irrespective of what method you're using, whether you're using Gauss-Jordan or the method of elimination and substitution. And right below that, I'm showing an example of an incorrectly ordered variables, which is that, right? X, Z, Y, that's out of order, right? Y, X, Z, that's out of order, or Z, X, Y. So we want to put those in order and make sure that all the constants are on the right side. And this is the proper order of variables. X, then Y, then Z. Okay, and right below that, there's also another example of the same incorrect form and correct forms for a system of 4 equations and 4 unknowns. In this section, the largest system that we will apply these methods to is a system of 3 equations, 3 unknowns. We will not deal with 4 equations, 4 unknowns, because the technique, no matter which technique you use, without technology, without the use of computers and other technological tools, bigger systems solving bigger systems becomes very laborious when we do it manually. Okay, so that's as high as we will go, is solving a system of 3 equations with 3 unknowns. Okay, the best thing to do with this, learning this content, is to just jump right in and start with an example. And we're going to apply the method of elimination and substitution, remembering that that method that we learned to use with 2 equations, 2 unknowns in the previous section will change a bit when we apply it to 3 equations, 3 unknowns. So the question is how? How will it change? Well, this is how it will change. See, with the 3 equations, 3 unknowns, we can't apply the elimination and substitution right away. We must reduce this system of 3 equations, 3 unknowns to a system of 2 equations and 2 unknowns. So we must make this system smaller in order to apply that method. Well, how will we do that? Well, this is the part that you're going to learn in this section. First, let's label each equation. So that first equation is equation 1, equation 2, and equation 3. Right? Now, with each pair of these equations, form a different system. So let's prepare 2 systems, 2 separate systems, each system with only a pair of these equations. And it's your choice which equation to choose for which pair of systems. And usually what I would do is I recommend that you use the easiest equation in both pairs of systems. Okay? That's what I mean is this. So one pair of these equations, let's take that as one of the equations, x plus y plus z equals 8. And then the bottom equation, let's pair that up with the middle equation, 2x minus 3y plus 2z equals minus 4. So that's one pair, right? So we paired up equation 1 and equation 2, right? Now form a second pair, this time with equation 1, which was the easiest equation among the 3. And this time the third equation. So 4x plus y minus 3z equals 6. Notice you could pair up equations 2 and 3 also. But I just chose to pair up 1 and 3 because I think that equation 1 is a neat, easy equation to work with. Okay? Because in the end, it makes no difference which pairs you use as long as you do the steps correctly. So once you pick the pairs like that, now you can choose which variable to eliminate from this pair. From the outset, you have the option of choosing either to eliminate either x or y or z variable. At this point, you do have that option. But once you make that choice for this pair of equations, once you decide which variable to eliminate from this pair, For the other pair, you do not have the choice. You must eliminate the same variable from this pair. So right now, I have the choice of eliminating x, y, or z. If I choose x to eliminate in this system, then for this second pair of equations, I have no choice. I must eliminate the x variable. If I choose y to eliminate from this pair, then I have no choice here. I must eliminate the variable y from this pair. I hope you're following what I'm talking about. So now, I'm looking at these, and all these variables have easy coefficients to work with. Let's eliminate the variable z from this one. Right? Now I have a choice, and I'm making that choice to be to eliminate variable z. Okay? In doing that, then I have to make sure that the variable z has coefficients that are equal but opposite in sign. So this is 1, this is positive 1, this is positive 2. I want to make this coefficient equal to this but opposite in algebraic sign. So I'm going to multiply the top equation by minus 2. When I distribute the minus 2 to everything in this equation, the z term will have minus 2 coefficient, which will add up to 0 when I add the two equations together. Okay, so let's see how that is. So minus 2 times all of that. Minus 2x, minus 2y, right? I'm distributing the minus 2 to each term. Minus 2z equals minus 16, right? Okay, the bottom equation stays the same. Like that. Okay, now let's add the two equations. As we intended, the z terms add up to 0. But look what happens. At the same time, the x terms add up to 0. We didn't intend that, but it's fine. If it happens, it's fine. So those two also add up to 0. So what we're left with is minus 5y, right? Minus 2y plus minus 3y is minus 5y, equals minus 16 plus minus 4, it's minus 20. Okay, so this, let's not solve for y because our objective was to create reduced equations. By reduced, I mean equations that don't have 3 variables in them anymore. They have a maximum of 2. In this case, we ended up with 1, which is even better. Okay, but we do not want, the objective of this step is to reduce this original system of 3 equations, 3 unknowns, to a system of 2 equations, 2 unknowns. And we did half of that, we have achieved half of that goal. So let's come to this pair. In this pair, we made the choice to eliminate z, right? So here we have no option. We must eliminate z for this pair. Okay, so the z term in this top equation has coefficient plus 1, and in this equation it has coefficient minus 3. So I want these coefficients to be equal to each other, but opposite in sign. So what I have to do is multiply the top equation by positive 3. Okay, so let's distribute the 3 into everything you see in that equation. We're going to get 3x plus 3y plus 3z equals 24. Right? The bottom equation stays the same. 4x plus y minus 3z equals 6. Okay, so let's add the two equations together. What do we end up with? Well, as we intended, 3z, positive 3z plus minus 3z, these two add up to 0. We intended that. That's a good thing. Then let's add the x and y terms. 3x plus 4x is 7x. And 3y, positive 3y plus y, it is 4y. And on the other side, we end up with 24 plus 6, it is 30, right? So let's call this one reduced equation A, and this one reduced equation B. So they are reduced, right? Now we have a maximum of 2 variables in this one and only 1 variable in that. That's great. So the next step is we're going to form a new system with these reduced equations. So we're going to form this new system, which is minus 5y equals minus 20, and then 7x plus 4y equals 30, right? Now we can, because this is a system of 2 equations, 2 unknowns, now we can apply the method of elimination and substitution we learned about in section 6.1. Now it's applicable. Before, when we had a bigger system, it was not applicable to that directly. So now that we have reduced equations, we can do that. So now, using that, let me use method of substitution. The reason I'm saying is that if you notice from this equation, the first one, we can solve for y and substitute in the bottom equation to solve for x. So using minus 5y equals minus 20, we end up with, let's solve for y, which means we have to isolate y, right? Is y isolated? No, it's got a negative 5 next to it. How do we get rid of that? We divide both sides by negative 5. So from this, what is the result? On the left, the negative 5 and negative 5 cancel out. We get y equals, on the right, negative divided by negative is a positive number. 20 divided by 5 is positive 4. So for y, we were able to find y equals 4. Now let's find x by plugging that 4 into this bottom equation. So using 7x plus 4y equals 30 and substituting, we have 7x plus 4 times 4 equals 30, right? So 7x, let me move this up a little bit. 7x plus 16 equals 30. Then we need to solve for x, which is to isolate x. So let's get rid of the 16. How? By sending it to the other side. When we send 16 to the other side, the positive becomes negative. So there. Then 7x equals 14. And of course, x needs to be isolated by dividing both sides by 7, right? So we end up with x equals 2. Great, so y equals 4 and x equals 2. How do we find z? Very easily. We can pick any of the original equations that has all 3 variables in it, plug in for x and y, and solve for z. I'm going to pick the first one because it's an easier equation of the 3. Okay, so using x plus y plus z equals 8, let's substitute for x and y with 2 and 4. Right? 2 plus 4 plus z equals 8. So we have 6 plus z equals 8, which means z equals 8 minus 6, right? Which is positive 2. And here we have the solution for z. Okay, so what is the solution of the system then? We combine all 3. This one, and this one. So the solution of the system, this is the final solution, is x, 2, comma, y, 4, comma, z, which is 2. That's the final solution of the system. Because this is x, comma, y, comma, z. That's the format of the solution. Okay? That's where that point in 3-dimensional space, not 2-dimensional, in 3-dimensional space, 2, 4, 2 is all those three lines intersect at that point. Okay. So do you see how the method of elimination and substitution changes here? We cannot apply that method directly because that method is designed for a system of 2 equations, 2 unknowns, not for 3 equations, 3 unknowns. And this is the technique we use, as I explained, how we reduce the system of 3 equations and 3 unknowns to an equation of to a system of 2 equations and 2 unknowns. Okay? Then we can apply the method of elimination and substitution. Okay? So we're going to do another example. If you haven't done this on the first example, please pause the video and solve this on your own and then come back to the video. So just write this down and solve it and then come back. Okay, so I'm assuming you've done that and you have your solution in front of you. Okay, so this is a system of 3 equations, 3 unknowns. We cannot apply the method of elimination or substitution directly at this point. So we need to break this up into 2 pairs, right? Let me label these. So that's equation 1, equation 2, and equation 3. So equation 2 is the easiest one of them all. That's why I'm going to incorporate or include equation 2 in both pairs of systems that I'm going to set up. So 1, we would have x plus y equals 5 with the first one, 2y plus z equals 5, and here once again x plus y equals 5, right? And the third equation. You don't have to do this. You can pair up the third and the first equation if you like. You'll get the same result as I do once we're both finished. Okay? All right. So let's decide which variable to eliminate from. Oh, I see. So here, if you look at this system, I wouldn't be able to eliminate x, right? Because x appears in one equation but not the other one. I wouldn't be able to eliminate z because z appears in this equation, not that. The only variable that appears in both equations is the y term. So even though normally you would have the choice as to which variable to eliminate, but in cases like this, you don't have a choice. Because of the way these equations are, you must eliminate variable y. No choice. Which means when we get to this side, we must eliminate variable y from this pair. Okay, so let's do that. To eliminate variable y, I must make sure that their coefficients are equal and opposite in algebraic sign. To do that, I'm going to multiply the top equation by -2. Okay. When we distribute the -2, what do we get? We get -2x, -2 times y is -2y equals -2 times 5, -10. Then the bottom equation stays the same. We end up with that. And then, of course, let's add those 2 equations. What happens is -2y and 2y add up to 0. So what are we left with? We are left with -2x plus z, right, equals -10 plus 5 is -5. So let's call this equation reduced equation A, right? So we eliminate the y variable in this pair. We have no choice but to do the same thing over there. Okay, let's do that. So to eliminate the variable y, I must make sure that the y terms have equal but opposite in sign, coefficients that are equal but opposite in algebraic sign. Therefore, I have to, with that goal in mind, I have to multiply the top equation here by -3. So what do we end up with? we end up with minus 3x minus 3y, right? I'm just distributing this, equals what should be on the other side? Minus 15, right? Then the bottom equation, 3x plus 3y minus z equals 16. All right, so let's add these two equations. As we intended, the y terms drop out, right? Like that. But it just so happens that the x terms also add up to 0, which is fine. So we end up with minus z on the left equals minus 15 plus 16. That's positive 1, right? Positive 1. So if we have minus z equals 1, so z is equal to minus 1, right? So our intention was just to find the reduced equation so we can pair it up with this reduced equation and form a new system of two equations, two unknowns, and then apply the elimination and substitution. But now, this was actually fortunate. It made our work a lot less. Okay? So let's substitute with these two results. In fact, this is our reduced equation B, right? So let's form a system. With that and with this, we end up with this reduced equation, which is minus 2x plus z equals negative 5 equals z equals negative 1. So let's substitute in that equation with negative 1. Right? That's all we have to do to solve for x, because we already know what z is. So using minus 2x plus z equals minus 5, minus 2x, right, plus z, which is equal to negative 1, equals negative 5. Okay, let's solve for x. So I'm going to move this negative 1 to the other side. It'll be positive when I move it, right? Negative 2x equals negative 5 plus 1. Then let's add those two together. We end up with negative 4. So from this equation, divide both sides. To isolate x, what do we have to do? Divide both sides by negative 2. On the left, we just have x. On the right, we have negative divided by negative is positive 2, right? So that's x. So z is equal to negative 1 and x equals 2. We have the variable y to solve for, right? So any of these three equations would do. Let's pick the easiest one, x plus y equals 5. Let's use that one. So using x plus y equals 5, we have x is 2, right? Let me bring this down so you can see. X equals 2 plus, y, just y, equals 5. So then move the 2 to the other side. It's positive on this side. When you move it to the right, it becomes negative. So y equals 5 minus 2. And that means that y equals 3. Okay? Okay, so now we have all the three solutions here. Let's write down the final answer. So the final answer, we have to match all of these, and the final solution is 2, 3, negative 1. Right? That's the final solution of that system. Those three lines intersect each other in three-dimensional space at this point. 2, 3, negative 1. Okay. All right. I hope this is making sense, and I hope that your own solution matches with what I have here. Okay, so finally we get to the method of Gaussian elimination. Now in this method, we no longer deal with, as you can see right from the top here, we no longer deal with variables, x, y, z per se, at least not directly, but we will deal with their coefficients. But remember, still x, y, and z must be ordered in the proper order. So x, y, z, and x, y, z, right? These variables still have to be in order, and even though we're going to use their coefficients, and the right side should be just constant. Okay? Sometimes when you read books, in books, some author would like to put a vertical bar here, which is okay. Placing this or not placing it is just a matter of preference. If it's missing, it's not that it's incorrect. If it's present, it doesn't mean that it should be. It's just a matter of preference. So you should be familiar with both. If it's not there, it means that those numbers are the constant values from the original system. It's very, very important for you to, even though the variables are not there, your mind should realize that these are the coefficients of those variables. You should keep that in mind as you go through this procedure. At the top, I have this small paragraph which I should actually mention something about. I'm talking about this paragraph. I think the best way to explain what that is saying is this. Let me draw this diagram, and I think that space is enough for me to make that point. I'm going to use the analogy of riding a bus, right? Suppose we want to get from point A, let's call this point A. Suppose we want to go from A to point B, to some point B here. Let's say that point B is here. Okay? We want to go on, we want to ride the bus to go from point A to point B. Now, suppose there is an option. Suppose there is an option of getting off the bus at an earlier station, let's say here. Let's say there is an earlier station here. Suppose we get off the bus at this station and then walk to a station B. Okay, so let's call this, since I call this, well, let me, for the sake of discussing this, let me call this C and this B. Okay, so in order, A, B, C. So our main goal is to ride the bus, to board the bus at station A and to get to station C. Now, we can either stay on the bus until the bus lets us off at station C, or we can get off station B and then walk the rest of the way to station to C, to our destination, right? So this earlier station where we can get off the bus and walk the rest of the way, it is called, in this Gauss-Jordan method, in this method of Gaussian elimination, this station, earlier station, is called the row echelon matrix. So let me write that here. Row echelon matrix. Okay, so when you solve a system, That's your intention at point A, right? To solve the system using the Gaussian elimination. We will talk about this. Don't worry about this. I want to make sure that you understand what these names mean. I'm talking about these names. The augmented matrix, the row echelon matrix, and the reduced row echelon matrix, okay? You need to know what these are. And you need to have a clear picture of what they are, okay? So the initial place where you board the bus, that's the augmented matrix, right there. That is the augmented matrix. That's where you will begin. The Gaussian elimination method begins with the augmented matrix. Okay? I hope this is creating a picture of what is going to happen in your mind. Okay? That's my goal. Then this destination C is the reduced row echelon matrix. Okay. So the Gaussian elimination, the diagram that you see is the overall picture of how the Gaussian elimination works. It's basically starting out with the augmented matrix. This is a matrix of coefficients. Like I was saying a few minutes earlier, look at this. This matrix has the augmented matrix that looks like that. Look at the numbers. They're not, first of all, the variables are in order, right? So the first column are the coefficients of variable x. Look back and forth between these two. The second column are the coefficients of variable y in these three equations. And the third column are the coefficients of variable z. And the far right-hand side, these are just constants. Okay, they're not coefficients of any variable. They're just constants. Okay, so when you use the Gaussian elimination, the method starts with the augmented matrix. So you start with this matrix of the coefficients of the original system. Is that clear? That's what the augmented matrix is. That's where you start applying the Gaussian elimination. First, you write up the augmented matrix, which is that. Then the method of Gaussian elimination, which we will talk about in detail, takes you through this journey, which I use the analogy of riding a bus. It takes you through this journey to one of two destinations. Your ultimate goal is to get to this point C. So this is the ultimate destination right here. That's the final destination. But you can either ride the bus all the way to C, all the way to the final solution or final matrix, which is called reduced row echelon matrix. That would be the final destination. Or you could stop at this station called row echelon matrix and do a little more work, which I use the analogy of walking the rest of the way. Okay, so you can get off the bus here at this station B and walk the rest of the way to station C. Station C is where the solutions of the original system are readily available, which is what happens when you have the reduced row echelon form, but not when you have row echelon matrix. Because that station, if you stop here, if you stop the Gaussian elimination procedure at this point, then you have to do a little more work to find the final solution, C. But if you write the Gaussian elimination all the way to reduced row echelon form, then you don't have to do more work. You simply, when you get to this matrix, you have solved the system. Okay? So this diagram should clarify what these are, what these terms are. The whole thing is applying the Gaussian elimination method. So the whole thing, the whole diagram represents this method. But at the beginning, the diagram begins with the augmented matrix and ends with either row echelon matrix or reduced row echelon matrix. Okay? We will talk about both, so you are familiar with both forms of destinations. What happens if you stop here, and what happens if you stop here? Here, if you stop, you don't have to do more work. You can simply read the solution off of the matrix. But you can't do that here. Here, you have to do a little more work to get to C. Okay? Your book uses these different names, so I'm using it, so that when you read the book, then you are clear what these terms refer to. All right, so we've talked about that. Now, let's talk about the augmented matrix. Before we get to the Gaussian elimination method, before we get to this method, I want to make sure that you know how or what these matrices look like. Okay? I want to talk about the details of this path, this journey in the last step. For now, I want to make sure that you know what an augmented matrix looks like, what a row echelon matrix looks like, and what a reduced row echelon matrix looks like. When I talk about this in class, every single time people say, well, how do you get from here to here, though? I say, that's an excellent question, but hold on to that thought. We're not for the next 10 minutes, we're not going to bother with the journey, which is the Gaussian elimination. We just want to know what these look like, each of these spots. A, B, C they look like. That's all we want to do. Okay? So, the augmented matrix is the matrix of coefficients. We already mentioned that. So look at this system and compare it with this. Look at the coefficients. 1, 1. Minus 3, minus 3. 3, 3. And minus 4 is the constant. In the second row, 2x, the coefficient is 2, right? 2. 3, 3. Minus 1, minus 1. 15, 15 in the constant column. 4, 4, negative 3, negative 3, negative 1, negative 1, and then 19. Okay, that's how you create the augmented matrix. You use the coefficients and the constants from the original system, not the variables. And this is the augmented matrix for a system of 4 equations and 4 unknowns. Notice that all the variables are in proper order. The constants are all on the right-hand side. So we have the first column, 1, 1, 1, 1. 1, 1, 1, 1, right? Look at the coefficients. They're all 1. So the coefficients of which variable do these ones represent? Which variable? x1, right? How about the second column? Which variable, the coefficients of which variable are these numbers? Which variable? x4, x3, which one? x2, right? That column. This column are the coefficients of variable x3. This column are the coefficients of variable x4. And the last column, these are just constants. Okay? Is this clear so far, how we set up the augmented matrix? All right, great. So now, let's talk about the row echelon matrix. What does it look like, right? I promise you that we will talk about Gaussian elimination procedure itself. But for now, I want to make sure that you know what an augmented matrix looks like, which we just discussed. And I want to make sure that you know what a row echelon matrix looks like and how we can use it to solve a system. So, the row echelon form of this augmented matrix. So this is the augmented matrix. That's the augmented matrix. And this is the row echelon matrix. Okay, so how are we going to use this? Like I explained in this diagram, if we get off the bus at this station, we can still solve the system, but we got to do a little more work. Or as I mentioned, we should do a little more walking to get to C, which is where we can solve the system. So how do we use this? First of all, what makes up this row echelon matrix? Why do we call this row echelon matrix and not that one? Okay, this is why. Notice the diagonal elements in this matrix. They're all 1, right? Also, notice below that diagonal, all the numbers are 0. So what I have highlighted in yellow is the reason why we call this matrix a row echelon matrix. The diagonals are 1. Below the diagonal, all the numbers are 0. Above it, they can be anything. It doesn't matter. But the highlighted part of that matrix is the distinct characteristic of row echelon matrix. There are, of course, special cases, but in this course, we won't get to those. Those of you who are math majors or intend to take classes like linear algebra or higher math classes, then you will get to special cases where row echelon form looks a little bit different than this. But still, it is called the row echelon matrix. Okay, so now that we know how row echelon matrix looks, how do we use it to solve the system? How do we use it to walk to a station C? Okay, so how do we do that? All right. Remember when I was explaining this, I marked each column with the variable that these numbers are associated with. Let's do the same thing here, and let's assume these were x, y, z. So the first column is associated with variable x, the second column associated with variable y, and the third column is associated with variable z, and of course these are the constants, right? Those are the constants. Okay, now starting from the bottom up, because this is what this is asking us to do. It says using the above row echelon form, can you solve the system? And the answer is absolutely yes. So how do we do that? Well, start from the bottom and rewrite the original system with the variables attached. What do I mean by that? Well, didn't we label each column with the variable that is associated with? So starting from the bottom, 1 times z, you can rewrite the original equation with the variable attached. Starting from the bottom, you say 1 times z is equal to -2. Right there, we have the answer for one of the variables just by writing the original equation using these numbers. So 1 times z, that's why I said you need to make sure that these variables are in order. If you didn't make sure of that, all of this would be mixed and it would be impossible to use the row echelon matrix to solve the system with. That's why the variables must be in order. So you know this column represents the coefficients of x in 3 different equations. This column represents the coefficients of y in 3 different equations. And this column represents the coefficients of z in 3 different equations. So starting from bottom up, rewrite the original equation with the variables. This is 1 times z is equal to the constant, -2. We're done with that. Then move up. We're moving from bottom up, right? So we did that. We used the third equation. We got that. Now let's move up to the second equation, which was, now we're going to use this row, these numbers, to write down the original equation in the system with the variables attached. Well, 0 times x is 0, so there's not going to be any x in this next equation. 1 times y, there's going to be a y, right? 1 times y is y, plus 4 times z equals negative 7. Okay? Great. So now we already know what z is, so let's plug in and find y. So y plus 4 times negative 2 equals negative 7. Then y minus 8 equals negative 7. And of course, from that, we get y equals negative 7 plus 8. Move the negative 8 to the other side. It becomes positive 8. And then, therefore, y equals positive 1. Okay? And that is y. So we know z. We've been able to use row echelon matrix, which has this distinct characteristic, as I've highlighted. Diagonals are all equal to 1. All the numbers below the diagonal are 0. That's the row echelon matrix. And we're using it to solve the system. Z equals negative 2, y equals 1. And then for x, move up another row, and using these coefficients and those variables, rewrite the original equation with all the 3 variables attached. So 1 times x is x, right? 2 times y, it's 2y. Minus 1 times z is minus z, equals to the constant on the other side, which is 1. Do you see that? Did you follow how I got this equation from those, the top row coefficients? Okay? So now we already know what y is. We know what z is. We can plug in here and solve for x. That's very easy, right? So let's do that. So x plus 2 times y, which is 1, minus z, which is minus 2, equals 1. Right? So let's simplify. X plus 2 minus minus 2 is plus 2 equals 1. So we end up with x plus 4 equals 1. And then x equals 1 minus 4. And then, of course, x equals minus 3. So using the row echelon matrix, we were able to find x, y, and z. So the solution of the system then, let me write it here. Let me write it at the bottom here, is minus 3, comma 1, comma negative 2. So that's solving the system using the row echelon matrix. Okay, so that's what I meant by doing a little bit of walking. Because we got off the bus a little early, right? We didn't go all the way to station C. So we had to do this much little work to finish the work and find the system. So that's what I meant when I said if you use row echelon matrix here, if you get off the bus here, you do a little bit walking to get to C. That's the little bit of walking that we did. Okay? Does it make sense now? Okay. So, again, to those of you who are wondering, how do we get from augmented matrix to row echelon matrix or reduced row echelon, hold on to that thought. We will get to it, I promise you. But for now, I just want to make sure you know what an augmented matrix looks like, you know what a row echelon matrix looks like, and how to use it to solve the system, which is what we just did. And lastly, what a reduced row echelon matrix looks like and how to use it to solve the system. Okay, that's the next topic. This is the reduced row echelon matrix. Of course, not this one. This is saying that the reduced row echelon form of this augmented matrix is that. Take a careful look at the reduced row echelon matrix. Do you see what are the dominant characteristics of that matrix, the reduced row echelon matrix? Do you see what are the dominant features of it are? Okay, so notice that in the reduced row, so well, let me label these first. This one, once again, is the augmented matrix. And this one is the reduced row echelon matrix. That's, if I bring back this diagram that I did, that's the last station. If we get off the bus here, we have finished solving the system. There is no more walking that we need to do. We are done. Okay, so let's see how that can be shown. So this is the augmented matrix. Suppose we start with that. After applying the Gaussian elimination method, which we will talk about shortly, we get to this reduced row echelon matrix. The dominant features of the reduced row echelon matrix is that, which I've highlighted. Notice that the diagonals are once again 1, but below that diagonal are 0, but also above it, all the coefficients are 0. Above the diagonal or below the diagonal, all the coefficients are 0. What you have in the last column, that is the constants, or also now the solutions of the system. Okay, so how are these numbers? This column is the solution of the system. Well, again, remember what this column represents. This column are the coefficients of variable x. The middle column are the coefficients of variable y. And the third column are the coefficients of variable z. So you can easily write down the solution as this question is asking, using the above reduced row echelon form, which is that one. Can you solve the system? Absolutely. 1 times x is equal to -3. The other numbers are zeros, so it won't give us any results. For y, I have to move to the second row. 1 times y is equal to 1, and 1 times z is equal to -2. So the final solution is -3, 1, -2. That's the final solution. From that reduced row echelon matrix, we can conclude that. Okay? I hope things are beginning to clarify. All right. So now, the question that you've been asking yourself many times, or me many times, right? But it's the video, so I get to talk and you're just watching now. So to move from the augmented matrix to either row echelon matrix or reduced row echelon matrix, we need to apply the Gaussian elimination, aka elementary row operations. Okay? So the question, of course, is what are the row operations? What are these? Which is the same name as that, right? Different name for the same method. What are the row operations that can help us find either the row echelon form or the reduced row echelon form? So here's the thing. There are various row operations you can use to solve a system. But I highly discourage you to use those operations that you see shown on the internet, in YouTube videos, in other places on the internet that might advertise or promote that kind of row operation. My experience is that if you're so skilled in solving systems using the Gaussian method, Gaussian elimination method, then you can use all these various strategies or row operations to solve the system with no issues with any kinds of obstacles that might be on your way, without any error, basically. You should be very skilled. But because I'm assuming that most, if not all of you, are seeing this for the first time, so we're just introducing this method, you want to restrict yourself to certain operations. For example, you want to be able to add rows but not subtract them. That's why I'm going to, right in front of you on this video, these are the various row operations we can do. I'm going to cross out the ones that I encourage you not to do. Also, books now are more mindful of what I'm talking about. In other words, even though the author knows there are many other various operations with which one can solve a system, they just promote the operations that they believe based on their experience, and I can testify that based on my experience, their work is good, that based on this experience, there are certain operations that you as the beginner of user of this method should use. So forget about subtracting rows from each other. You should always add rows to each other, because subtracting rows is filled with problems. A lot of you might have issues with distributing a negative sign, for example, into a parenthesis. I still see that on exam papers, that people have difficulty distributing a negative into a parenthesis that comes after it. Now, with matrices, if you subtract rows, which is one of the valid row operations, if you subtract rows, you're distributing the minus into several terms and then adding those numbers to another row. And that's just too many distributing of the negative sign, negative algebraic sign, which I do not recommend. So let's see what are the row operations that I do recommend, and your book also follows that. We may interchange rows, and I will talk about what that means. We may interchange rows when there is a use for it. Not randomly, that means. Not randomly, but when there is a use for it. The use is usually to obtain the pivot 1 for each row. Remember when we were talking about the reduced row echelon and also row echelon, we talked about the diagonal ones. Each of those ones is called the pivot 1. Okay, that's the pivot. In this row, that's the pivot. In this row, that's the pivot. Okay, that's the terminology we use for it. So it might be useful to interchange rows to obtain the pivot 1. That's one use of interchanging rows, while keeping any previous work intact. Okay. Second operation that we're allowed to use, we may use the pivot row to add or subtract rows when applicable. So we might use the pivot row to add. I want to highlight that, and I want to get rid of this, and I'm going to use my thick marker to say not subtract. Let's get rid of that. We do not want to subtract rows. We always want to add rows to each other. Notice I used another terminology here. Here we have pivot 1. Here we have pivot row. All of these are very important in applying the method of Gaussian elimination. Okay? So, we may use the pivot row. I'll talk about that pivot row. Basically, it's the same row that has the diagonal 1. So for the first row, that's the pivot row. Second row, it's that, because we have a diagonal 1, and so on. So any row that has a pivot 1, it's the current pivot row. Okay? And after solving some examples, you see exactly how that works. So we may use the pivot row to multiply or divide. That's the divide, again, is another term I'd like to eliminate. And books nowadays, they also do not like to use subtraction or division. They'd rather you to add and multiply, because adding and multiply not only are valid row operations, but there is less probability of you making error when you multiply or add than when you subtract or divide. Okay, that's why. So we may use the pivot row to multiply a row by an integer when applicable. And will applicable before, let me add something to this, before adding the pivot row to the row we intend to change. Okay? So those are the three basic row operations that I'd like to encourage you to use. Do not use subtraction. Do not use division. If you comb through the solved examples on the internet, quite often you see the presenter using all these operations, adding, multiplying, dividing, subtracting. Because you are new to this procedure, I strongly encourage you to stay away from any presentation of this method that asks you to subtract or divide rows by each other, or divide numbers by each other. Okay? Just stick with interchanging rows, adding rows, and multiplying rows. And let me also highlight the multiply, the word multiply here. Multiply, add, and interchange rows. And of course, this should be added to the end of this before. So we may use the pivot row to multiply a row by an integer when applicable before adding the pivot row to the row we intend to change. Okay. All of this is just for the sake of your notes, but this methodology is best understood when we actually do solve one of these. And even though this method is used to solve bigger and bigger systems, I thought to start you off with an easy example of 2 equations, 2 unknowns, such that if you follow this one short example, one small example, then you can certainly handle bigger examples, okay? But just remember, Gauss-Jordan is mainly used with bigger systems, not smaller ones. All right. So here they're saying using the Gaussian elimination method or elementary row operations, solve each of the following systems. Well, do you remember when I was talking about that diagram, where does the Gaussian elimination begin? It begins with the augmented matrix, right? It begins with that. So let's write down the augmented matrix for this. So the coefficients, 3, -5, and 9, 1, -2, and 2. And I personally like to put a vertical line there to separate the coefficients of the variables from the constants. Okay, I personally like to use that vertical bar. All right, so now our objective is, I'm going to solve these examples going all the way to reduced row echelon matrix. So I'm not going to get off the bus early and walk the rest of the way. I just showed it to you how you can use it to solve a system, but I personally prefer to go all the way to take the Gaussian elimination method all the way to reduced row echelon matrix. Okay? Because that reduced row echelon matrix has other applications in linear algebra. It has more use than the row echelon form. All right. So what does the reduced row echelon form look like? How does it look for this 2 by 2 or a system of 2 equations, 2 unknowns? How would it look like? Where it would look like this: 1, 0, 0, 1, and the constants on the other side. So the constants, those numbers are debatable. What they could be, what they should be, that's debatable. They can be anything. But on the left, when we're done, the reduced row echelon form is just that. It cannot be anything different. So our objective is to take this augmented matrix to that destination where the reduced row echelon form is shown. So 1, 0, 0, 1, diagonal 1 is present, and any numbers below and above it are zeros. Okay? So, one of the greatest misnomers in mathematics is that this method is called the row operations. So despite the fact that we call it elementary row operations, despite that name, despite the name, we sweep column to column with the pivot 1 is the first number to obtain in each column. This is an extremely important thing that I added here. Extremely important. You don't have to understand it now, but as we go through the procedure, you must understand it. If you don't understand this little sentence that I wrote here, then this procedure becomes very difficult for you to follow. But despite the the name that is called the row operations, despite the name, we sweep column to column, right? So what do I mean when I say sweep column to column? So this is the augmented matrix. This is our destination. This is the starting point. This is the destination. We want this matrix to look like that. We do not care what numbers are on that side until the very end, but the left side should look like that, not like this, like that, because we're trying to solve this system. Okay? So when we apply this procedure that we just talked about, interchanging rows, adding the pivot row, use the pivot row to add rows when applicable, and multiply a row by an integer when applicable before adding the pivot row to the row we intend to change. As we do this, these 3 steps, our goal is to make the left side of this matrix, by that I mean left side of this vertical bar, to look like the left side of this reduced row echelon matrix. This should look like that. When we do that, we must sweep column to column. That means we finish this column to make it look like that. When we're done with this column, we move to the second column and we make it look like that. That's what I mean. Okay? So it is called row operations because we do use row operations. We add rows to each other. But what we're doing, the purpose of adding these rows is to sweep column to column, to make this column look like that, then move to the second column and make this column look like that, keeping in mind that the pivot 1, that in each column, the pivot 1 is the first number to obtain, then we worry about other numbers in that column. So when we sweep in column 1, the first number to obtain is this 1. Then we worry about how to obtain a 0 there. In the second column, we worry about obtaining 1 first. After we obtain the 1, then we worry about obtaining the 0 in that column. Okay, is that clear? Okay, so let's go over this example. Our objective is to convert this left side to that. Which one of these operations, you can still see them on your screen, which one of those three operations can I do to obtain a 1 in this corner? Because I want to make this look like that, right? I need to have, and we sweep column by column like I explained here, with the pivot 1 to obtain first. So in this first column, I must obtain this 3 as a 1. I must obtain a 1 there, not a 3. Which one of these I can use to achieve that, to get a 1 in that corner? Do you see it? Which one is the easiest one? One of those methods one of the row operations we can use is interchanging rows, right? Can you apply that here? Certainly. Because all we need is a 1 in that corner. Now we have a 3. But there is a 1 in this row, right there. If I interchange row 2 and 1, I'm going to end up with a 1 in that corner. Let's do that. So interchange row 1 and row 2. Let me use this notation. Row 1 and row 2, interchange them. With a double-headed row, I mean interchange row 1 and row 2. Okay, let's do that. So we end up with 1, -2, vertical bar, 2, and then 3, -5, and 9. Right? Now compare this with that. Did we get in the first column, and we sweep column to column. In the first column, did we get the 1? Yes, we did. So interchanging rows was a wise decision. We got what we wanted. Now what do? I'm asking you, sitting at home watching this video, what are you going to do next? Remember what I said here. We sweep column to column with the pivot 1 is being the first number to obtain in each column. So, will you then compare this with that? Are we done with the first column? No. We got the 1, but what about the 3? The 3 needs to become 0. Right? Can you multiply the second row by 0 and get it to be 0? No. Because that makes everything 0, and that's just not acceptable. Okay? So what else can we do? Well, notice that as soon as you obtain a diagonal 1, and these are called diagonal 1s, as soon as you obtain one of those 1s, the row that contains the diagonal 1, the row that contains it, it's called the pivot row. So now we have row 1 as the pivot row, right? So what we can do is use the pivot row to make this 3, 0. Well, how are we going to do that? Well, all we need to make this 3, 0, all we need is to have a -3 and then add it to this 3. -3 plus 3 is 0. And we will do this operation. We may use the pivot row to add. Okay? All right. Well, how are we going to get -3 then? Well, you have the pivot row, right? So if you multiply to change row 2 is equal to multiply the first row, which is the pivot row, by -3, so -3 row 1 plus row 2, it's going to give you a 0 in that spot. Okay? So that's why we call this row operation, but our objective is to sweep column to column. And we're almost done with the first column, but not yet. We need to carry out this row operation. We need to multiply the first row by -3 and then add it to second row. Let's do that. The first row isn't changing, right? The first row is the pivot row. So 1, -2, and then 2. So now let's carry this row operation. minus 3 times row 1, minus 3 times 1 is minus 3, plus row 2, minus 3 plus 3, 0. Minus 3 times minus 2 is positive 6. Positive 6 plus negative 5, 1. Minus 3 times 2 is minus 6, plus 9 is positive 3. So now, compare this, what we have, with the reduced row echelon form. And we sweep column to column with the diagonal one first, obtained first. Are we done with the first column? Compare that with this. Are we done with the first column? We are done, right? We wanted 1, we started with 3, 1, but we wanted 1, 0, 1, 0. We are done with the first column. Okay, let's move to the second column. Okay, like I said, we sweep column to column, like I said here. All right? Okay, so in each column, we start with the diagonal 1 first. We obtain the diagonal 1 first. But fortunately, we already have it. So we don't need to do anything to obtain a 1 in this spot. It's already there. Fantastic. Sometimes we get lucky, right? And that's good. So 1 is already there. So what do we need to do next? As you sit at home, watch this video, what do we need to do next? Well, our objective is to make the left look like that, right? And we sweep column to column. We just got the 1, so what do we need to do now? Convert the negative 2 to 0. Okay, how do we do that? How do we get, right now we have negative 2. How do we get 0 in that spot to make this column look like that, 1, 0? Well, all we need is a positive 2 to add to this negative 2 and get it to be 0. Well, fine, but where is this positive 2 going to come from? Well, we just got the diagonal 1 for this, right? We just got that. So that row is now the pivot row. To get our positive 2 that we need to add to this row, use the pivot row. So all we need is multiply this row by positive 2. That's going to give us 2, positive 2 in this spot. And then add it to the first row to change it. Okay? Let's write down that row operation. So we're going to change row 1, right? As we change this minus 2 to 0, we are changing row 1. So row 1 is equal to 2 times row 2, which is now the pivot row, plus row 1. Okay? If we multiply the second row by 2 and add it to row 1, we're going to get a 0 in that spot. Let's do it. I'm going to do that right underneath it because there's enough room, fortunately. So twice the second row plus row 1. So 2 times 0 is 0, plus 1, 1. 2 times 1, I'm just carrying out this row operation. 2 times 1 is 2 plus row 1, which is at this point is minus 2, 0. 2 plus minus 2 is 0. 2 times 3 is 6. 6 plus 2, 8. Okay? Now, let's write down the pivot row as it was, 0, 1, 3. Now, let's compare this with that reduced row echelon form. Okay? This looked at this compared with that. Are we there yet? Are we done? We are done. We are done because the left side looks like this left side, And the solution, those question marks that I put up here, are now 8 and 3. So the solution of this system is x comma. So remember that these columns are the coefficients of variable x, and this second column are the coefficients of variable y. So x equals 8. X equals 8, and y, 1 times y is y equals 3. Therefore, the solution is 8 comma 3. Oops. 8 comma 3. That's the solution of the system. Okay. Is this making sense, guys? So you need to, as we go through this procedure, you need to always think about this reduced row echelon form. This is your objective. This is that station C that I drew the diagram about when we were talking about that diagram. That's the final destination. And we sweep column to column, in each column with the diagonal 1 obtained first before we worry about the zeros. Okay. Next example. So here we are with another system, and we'd like to use the method of Gaussian elimination to solve this system. Now, please pause the video and start with the augmented matrix. I mean, you don't have to pause the video if you don't like to. You can pause the video, write down your own augmented matrix, and then unpause the video and watch what I've done. So instead of pausing the video and finishing the solution all at once, you can pause the video and before I do something, you do it. Okay? And that's what I want you to do. To first give yourself the opportunity to generate the solution for this before you see me work out the problem. You already know that that's the way to learn anything, right? You got to let your mind think through a problem before you see someone else do that. Okay, so I'm assuming you've done that, but what I'm saying really is please feel free to pause the video at every juncture before I do anything. You do it, then watch me do it. Okay? So the augmented matrix for this system are all the coefficients, right? So we have 1, 1, 1, the vertical bar, 8. Then we have 2, -3, 2, -4. Then we have 4, 1, 4, 1, -3, and 6, right? So remember, these are the coefficients of variable x. This column are the coefficients of variable y. This column are the coefficients of variable z, and these are the constants. So we have boarded the bus, so to speak. Remember that diagram? We've created the augmented matrix. We have boarded the bus. Now we're going to carry out or implement the Gaussian elimination method and get to the final answer. So what is our objective when we apply the Gauss-Jordan method or Gaussian elimination? Well, our objective is to get to this reduced row echelon form, that one. Right? We want to look at the left side. The right side over there on the constant side, we don't care what those numbers are until the very end. In the middle, what they are does not interest us at all. Only at the end, only when we have the left side converted to this form, to this look, and I mentioned before, a lot of mathematics is visual. So when we have finished converting the left side, column by column, to this form, then we care about what numbers are on the right-hand side, but not in the middle. In the middle, they can be anything. We ignore them. Okay? All right. So the first thing is, in the first column, remember, we sweep column to column by column, right? So we should have 1, 0, 0. Do we have, in that column, the first number we are concerned with is the diagonal 1. So is the diagonal 1 there? Yes, there is. It is right there. Okay, so as soon as we establish that, which row becomes the pivot row? The first row. The first row is the pivot row right now, because we got the diagonal 1. So this is the pivot row. You do not have a pivot row until you get the diagonal 1 established. It's very, very important for you to remember. Okay? Only because this was already 1 in that column, I could call that row a pivot row. Okay? All right, so now, what do we need to do next? What would you do next? Well, we sweep column to column. So are we done with the first column? Compare this column with that column. Are we done? No. There is 2 and 4. We need to convert 2 and 4 to zeros. Well, how are we going to do that? Okay. For converting the 2 to 0, to that, all we need is to add a negative 2 to it, right? And for converting 4 to 0, all we need is a negative 4 to add to this to get it to 0. Well, okay, fine. Where are the negative 2 and the negative 4 to be added to this row and this row are going to come from? Okay, we have a pivot row, don't we? We can multiply this row, the pivot row, by an appropriate value, such as negative 2 for the second row and negative 4 for the third row, and then add that result to the second row and third row in turn. Okay, so what do we need to do to get a negative 2 from the pivot row? How do we get a negative 2 from it to add to this? Well, first of all, to make this 2 to 0, we're going to change row 2, right? We're going to have to change to row 2. So row 2, let's write down the row operations first. Row 2 is equal to minus twice the pivot row, which is row 1, minus 2 times row 1, minus 2 times row 1, plus row 2. Okay, that's going to give us a 0 in that spot. Well, how are we going to make this 4 equal to 0? Well, this 4 is in which row? In row 3. So we're going to have to change the entire row 3. How? Well, we're going to multiply the first row, or the pivot row, by negative 4 and add it to the third row. So negative 4 times row 1 plus row 3. So those are the two operations needed to give us that first column. Okay? All right, let's do that. So now it would be a great idea for you to pause the video and write down the next matrix. You already have the row operations showing on the screen. So pause the video, write down the next matrix. You can see the previous matrix, the row operations. Write down the next matrix before I write it down. Okay? All right, so I'm assuming you've done that, and now you're back. So the first row isn't changing, right? It's row 2 and row 3 that are changing. So I'm going to write down row 1 as it is. 1, 1, 1, 8. Okay? All right. So now let's apply this row operation. So this row operation says multiply row 1 by negative 2 and add it to the second row. So minus 2 times 1 is minus 2. Plus 2, 0. Minus 2 times 1 is minus 2. Plus negative 3, negative 5. Minus 2 times 1 is minus 2, plus 2, 0. Notice I'm just carrying out this operation. Minus twice times row 1 plus row 2. Minus 2 times 8 is minus 16, plus row 2 is minus 20. Right? I hope this is so far what you have on your paper. How do we get row 3? Okay, this is saying multiply row 1 by negative 4 and then add it to row 3. Okay, so let's do that. Negative 4 times 1 is negative 4 plus 4, 0. Negative 4 times 1 is negative 4 plus 1, negative 3. Negative 4 times 1 is negative 4 plus negative 3, negative 7. Negative 4 times 8 is negative 32 plus positive 6 is minus 26. Okay? Is this the result that you have? If yes, fantastic. If not, take a close look and make sure that your answers are correct. And if you double check and you don't find any error in your solution, then probably my solution is incorrect. Okay, then let's look at my solution, and if you find an error, please let me know. Okay, it's quite possible that this is tedious procedure. It's quite possible that I make an error too. Okay, so now compare the first column with the first column in the reduced row echelon form. Are we done with the first column? Yes, we are, right? We are done with the first column. 1, 0, 0, 1, 0, 0. So what do we do now? We move to the second column, to this column. In each column, which number should we obtain first? The diagonal 1, right? We don't have diagonal 1 for the second row, do we? What is there instead? Negative 5, right? Negative 5 is there instead of 1. So in this second column, the first thing we must do is to, before worrying about this 0 and this 0, we must first obtain this 1. Okay? So how are we going to obtain a 1 when we have negative 5 there? Well, we can multiply that whole row by negative 1 over 5. So let's do that. So row 2 is equal to minus 1 over 5. That entire row 2, we multiply it by negative 1 over 5. Let's do that. So go ahead, pause the video, write down the next matrix before you see my solution there. Okay? All right. So only the row 2 is changing. Row 1 and row 3 are not changing for now, right? So let me write down row 1 first. 1, 1, 1. Vertical and 8. Now we're going to carry out this I forgot to say minus 1/5 times row 2. Okay, sorry about that. There it is. So we're going to replace row 2 by minus 1/5 of itself. Okay, so minus 1 over 5 times 0, 0. Minus 1 over 5 times negative 5, that's positive 1, which we intended. Negative 1 over 5 times 0, 0. Negative 1 over 5 times minus 20, it'll be positive 4, right? And let me write the bottom equation, or the bottom row. 0, negative 3, negative 7, negative 26. Okay? All right, so now compare this matrix with that. In the second column, did we obtain the diagonal 1? We did, didn't we? Right there. So as soon as you establish that, then this becomes your pivot row. That row that contains The row that contains the current pivot element, is called the pivot row. Okay, why is it important to establish which row is the pivot row? Well, because compare this with that. Are we done with the second column? Does the second column here look like the second column here? Absolutely not, right? What are the numbers that are not matching? The 1 should be 0, and the -3 should be 0, right? So, in order to make the 1 and -3 equal to zeros, we need to use the pivot row to achieve that. That's why it's so important to, as we move through the Gauss-Jordan method, for you to always know which row is the pivot row and so on. Okay? All right, so let's use row 2, which is the pivot row, to convert the 1 to 0 and -3 to 0. Let's do that. Row 1, this one that we're going to change in here is in row 1, right? Row 1 is equal to, all we need is to add a -1 to this, right? But where is the -1 going to come from? It's going to come from multiplying the pivot row by -1, so -R2 plus R1, which is the row we're changing. Okay? All right. So let's do that. And by the way, we also need to convert this -3 to 0, right? So what is the row operation to convert the -3 to 0? Well, all we need is to add a +3 to this -3. Okay, fine. But where is the +3 going to come from? The +3 is going to come from multiplying the second row by 3 and adding it to the third row. Okay, so row 3 is equal to 3 times that, 3 times row 2 plus row 3. All right, so let's carry out these row operations. Here, once again, I want to encourage you to please pause the video. You have the above previous matrix. You know which row operations you need to apply. Pause the video, please, and apply that to obtain the next matrix. Then come back to the video. Okay, so I'm assuming you've done that already. So row 1 is changing according to this row operation. -1 times row 2 plus row 1. Okay, -1 times 0 is 0. Plus 1, 1. -1 times 1 is 1. -1. Right? -1 times 1 is -1. Plus 1, 0. -1 times 0 is 0. Plus 1, 1. -1 times 4 is -4. Plus 8 is +4. Okay? So we got this operation done. Let's move to the next row operation. Okay, so this is saying, the second row, by the way, is the pivot row, right? It's not changing, so let's write it down. 0, 1, 0, and 4. So this row operation says, multiply the pivot row by 3. The pivot row is the second row. Multiply the pivot row by 3 and add it to row 3. Okay, multiply the second row by 3 and then add it to row 3. So let's do that. 3 times 0 is 0, plus 0, 0. 3 times 1 is 3, plus -3, 0. 3 times 0 is 0, plus -7, it's -7. 3 times 4 is 12, plus -26, it is -14. Okay? Does this look anything like your matrix? If it does, fantastic. That's what I've been looking for. Okay, so now, since it's off the screen, let me write this again here so you can look at it. This is the reduced row echelon form. Okay, so you have it here now. Compare this with that. Is the second column done? It is done, right? We wanted 1, we wanted 1, we got 1. We wanted zeros above and below that 1, we got zeros above and below that 1. So we're done with the second column too. What about the third column? Is it done? Absolutely not, right? We need to have, in this column, we need to have a 1 here and 2 zeros above it. And in that column, we need to find, the rule is that we need to convert this to obtain the 1 first. So how do we obtain a 1 there? It's -7. Well, we can multiply that whole row by -1/7. Like that. Okay? So let's do that. And again, please make sure that you pause the video and write down your own matrix before you see my solution here. Okay, so because row 3 is changing, row 1 and row 2 stay the same, right? So let's write them down. 1, 0, 1, 4, and then 0, 1, 0, 4. And now let's apply this row operation. -1/7 times 0, 0. -1/7 times this 0, 0. -1/7 times -7, +1. -1/7 times -14, it's +2. Right? So compare this with the reduced row echelon form here. Did we obtain the diagonal 1 in that column? Yes, we did, right? Right there. We did that. As soon as you establish that, the third row becomes, what does it become? Do you see that? Do you know what I'm going to write down? Pivot row. Why is it important that we identify pivot row? Because to change any other number in that column, we must use the pivot row. So we need to know which row it is. Okay, it's that one. All right, so compare this side, the left side, with the left side of the reduced row echelon form of a matrix. Are we done with column 3? Almost, but not quite, right? So what number should be converted? Did you think about that? What should be our next step? Well, the next step is we do have 1 and 0, 1, 0. So, but this 1 here needs to also be converted to 0, right? We can do that by adding a -1 to this. Well, where is the -1 going to come from? It's going to come from multiplying the pivot row by -1 and adding it to the first row. So multiply the third row by -1 and add it to the first row. Let's do that. So row 1, which is the row we're changing, right? Because that 1 is in row 1. Row 1 is equal to minus row 3, or -1 times row 3, which is that, minus row 3, plus row 1. Okay? Great. So let's write down the next matrix. And I'm counting on you to pause the video and write down your matrix before you look at my solution. Okay, so -1 times row 3 plus row 1. -1 times 0 is 0, plus 1, 1. -1 times 0 is 0, plus 0, 0. -1 times 1 is 0. -1 times 1 is -1, plus 1 is 0. -1 times 2 is -2, plus 4 is +2. And the other two rows, let's write them down as they are. 0, 1, 0, 4, 0, 0, 1, 2. Now, go ahead, compare the left side of this matrix with that. Do we have the reduced row echelon form matrix? 1, 0, 0, 1, 0, 0. 1 0 on top and 0 bottom, 1 0 0. We do. 1 at the bottom and 2 zeros on top, 1 at the bottom, 2 zeros on top. So we got it. We have the reduced row echelon form. So now we can write the system solution here, right? Remember that these numbers are the coefficients of variable x. These numbers are the coefficients of variable y. These numbers are the coefficients of variable z. And these are the constants, right? So the solution is x. 1 times x equals 2. 1 times y is equal to 4. And 1 times z equals 2. So putting this answer in proper form, the answer is 2, 4, 2. And that's the final solution of the system, using the Gauss-Jordan method or the Gaussian elimination method or the elementary row operations. Okay, I hope this was useful. All right, so let's look at another example here. So go ahead, write down the augmented matrix for this one. And before you do that, I'll give you a hint. I'll give you a hint here. Any missing term you cannot skip. You must put 0 in the augmented matrix for it. Okay, that's the only hint I'm going to give you as you pause the video and you write down the augmented matrix for this. Okay, so let's do that. So in the first equation, x is missing, right? So 0. The coefficient of y is 2. Coefficient of z is 1. And then the constant on the other side. How about the second row? Well, x is present with the coefficient 1. Y is present with the coefficient of 1. Z is not present. Can we skip it? No. We're just going to have to put a 0 for it, for z, for the coefficient of z, that is. And then 5 on the other side. And then at the bottom, we have 3, 3, minus 1, and then 16, right? That's our augmented matrix. Remember, our objective is to go from here to this format. 1, 0, 0, 0, 1, 0, 0, 0, 1, and the right-hand side, whatever those values will be the coefficient, the solution of the system. Okay, so among the row operations that we are allowed to carry out, which one would you do? So our objective is to get a 1, to start with the first column, and to get a 1 in that corner. Do we have that? No, we have a 0. What can we do to get a 1 in that corner? Well, remember, one of those things, one of those row operations we can do is interchange rows, right? Should we do that here? Would it be useful? Absolutely. If you swap row 1 and row 2, you're going to get a 1 in that corner. So let's do that. Swap row 1 and row 2, or interchange them. Okay, we have 1, 1, 0, 5, right? Row 2 moved up. Now row 1 comes to the middle. 0, 2, 1, 5. And row 3 is 3, 3, minus 1, 16. It remains where it was. All right? Now what do we do? Compare this first column with the first column there. What do we need to do? We need to convert this 3 to 0, right? Okay, let me ask you this. Which row is the current pivot row? Do you see it? Which of these rows is the current pivot row? Well, if you said the first row, you're absolutely correct. The first row right now is the pivot row. Why is that? Because we just got the diagonal 1 for it, right? We just got the diagonal 1. Why is it important for us to ask this question and establish which row is the pivot row? Well, because as we want to convert this 3 to 0, we need to use the pivot row to achieve that. All right? And the first row is the pivot row. So how do we get a negative 3 to add to this positive 3 to get it to be 0? We can get the negative 3 from the first row by multiplying the first row by negative 3 and adding it to row 3. Okay, let's write down the operation for that. So the 3 that we're changing to 0 is in row 3, right? So we're changing row 3. Row 3 is equal to minus 3 times row 1 plus row 3. Okay? I hope you agree with that row operation. Now would be a good time to pause the video and write down the next matrix for this. Okay, I'm assuming you've done that, and now you're back. So row 1 is the pivot row, so naturally it's not changing. Row 2 is not changing either because we already have a 0 in that spot. So 0, 2, 1, 5. Now we're going to change row 3 with this row operation. Minus 3 times 1 is minus 3. Plus 3, 0. Minus 3 times 1 is negative 3. Plus positive 3, 0. Minus 3 times 0 is 0. Plus negative 1 is negative 1. Minus 3 times 5 is 15, is minus 15. Plus 16 is positive 1. Okay? So compare the first column with the first column in the reduced row echelon matrix. Are we done with the first column? We are, aren't we? 1, 0, 0, 1, 0, 0. Okay, so we sweep to the second column now. In the second column, where do we want, what do we need to do? Compare this with that, and what do we want to do for the second column? Well, what number do we want to change? We want to change 2 to 1, right? Remember, as we sweep column to column, the number in each, the first number to obtain in each column is the 1, is the diagonal 1. So we need to convert the 2 to 1 before we worry about converting any other number to 0 there. Okay? Well, how can we convert the 2 to 1? Well, we can multiply the second row by 1/2. Let's do that. So row 2 is equal to 1/2 row 2. Writing down the next matrix, we have 1, 1, 0, 5, and then multiply the second row by 1/2. 1/2 times 0, 0. 1/2 times 2, 1. And this is our pivot element right now, right? This is the pivot element, which will then identify the pivot row. All right, so 1/2 times 1, 1/2. 1/2 times 5, 5/2. And the third row isn't changing for now, so I'm going to write it down as it is. Okay, so it's off the screen now, so let me write it here again so we can look at it. This is the reduced row echelon form, right? Compare this with that. We're in which column? Second column, right? We just obtained the diagonal 1. We just obtained that one, right? So, in that case, the second row becomes our pivot row, doesn't it? That one is pivot row. Okay? Why was that important? Why did I highlight it? Well, in the second column, what do we have to do next? We have 1. We needed 1 in the diagonal position. We have it. We needed a 0 in the bottom, we have it. We need a 0 on top, we don't have it. We just got a 1. So to convert that positive 1 to 0, we need to use the pivot row, and the pivot row now is the second row. All right, so how do we convert this 1 to 0? All we need is add a negative 1 to this, and we get it. We get a 0 in that spot. But okay, fine, but where is the negative 1 going to come from? The negative 1 is going to come from multiplying the pivot row by negative 1 and adding it to the first row. Okay, let's write down that operation. So we're changing row 1, right? So row 1 is equal to minus row 2, that's this row, plus row 1. So that's the row operation for that. So please pause the video and write down the next matrix before you see my matrix here. Okay, I'm assuming that you've done that and now you're back. So let's carry out this operation. Minus 1 times row 2 plus row 1. So minus 1 times 0 is 0, plus 1 is 1. Minus 1 times 1 is minus 1, plus 1, 0. Minus 1 times minus 1 half is minus 1 half, plus 0 is minus 1 over 2. Minus 1 times 5 over 2 is minus 5 over 2, plus positive 5, it is positive 5 over 2. Okay? Just take the common denominator, right? So you have, when you multiply the second row by minus 1, you get, what do you get? You get minus 5 over 2, right? Then you're adding that to the first row because we were doing this operation. So minus 5 over 2 plus 5. Then take the common denominator. You get negative 5. That common denominator is that. The common denominator of 5 is 1. How do you get it to 2? Well, you multiply the numerator and the denominator by 2. So you're going to get 2 times 5 is 10. 10 minus 5 is positive 5 over 2, which is what we have here. Okay? So now do you see where the 5 halves is coming from? Minus 1 times 5 over 2 is minus 5 over 2 plus 5 plus row 1. And then take the common denominator to get that. Okay, so now the second row, we can write it as it was, 0, 1, 1 half, 5 over 2, and the third row is 0, 0, negative 1, and 1. Okay, now compare this side with that side, with the reduced row echelon form. Are we done with the second column? Are we? We are, right? We needed a diagonal 1, we have it. We needed a 0 on top, we have it. We needed a 0 on the bottom, we have it. So we're done with the second column. We sweep to the third column. Next one over, right? Okay, so now compare this third column with that third column. What would you do next? Remember, the diagonal 1 should be obtained first. So don't worry about converting these two to zeros yet, because your task is convert this negative 1 to 1, positive 1. How are we going to accomplish that? Well, very easily. We can multiply the third row by negative 1. It'll make that negative 1 positive 1. Let's do that. So row 3 is equal to minus row 3, right? So let's write down the next matrix, and I prefer that if you would please pause the video and do that on your own. So that means row 1 and row 2 are not changing. Let's write them down as they are. Minus 1 times 0 is 0. Minus 1 times 0 is 0. Minus 1 times minus 1, positive 1. Minus 1 times that 1, minus 1. Okay? All right. So now what do we have to do next? Compare this with that, right? It's still on the screen. So, like that. Compare this with that and decide what you need to do next. So, we need to have a 0 right above 1. Do we? No. We need to have a 0 right above that, above the second row. Do we have that? No. So we need to convert these two numbers to zeros. Okay, before that, let me ask you, which row now in this matrix, which row is the pivot row? If you said the third row, you're absolutely correct, because we just got the diagonal 1 for it. So this third row is the pivot row. Okay. All right. So why is that important? Because in order to change, as we agreed, we need to change these two numbers to zeros, right? Right, like that. In order to change these two numbers to zeros, we need to use the pivot row, which is now row 3. Okay, so let's write down the row operations necessary for accomplishing that. And I'm going to do that here. Okay, like that. Maybe I can keep everything on the screen as much as possible, like that. Okay. All right. So to change this negative 1/2 to 0, all we need is add a positive 1/2 to it. Okay, fine. But where is the positive 1/2 going to come from? The positive 1/2 is going to come from multiplying the third row or the pivot row by positive 1/2 and then adding it to the first row. So row 1, which is the row we're changing, right? Because negative 1/2 is in row 1. So row 1 is the row we're changing, is equal to 1/2 times row 3, right? Multiply the third row by 1/2 and then add it to the first row plus row 1. So that's the row operation to changing the negative 1/2 to 0. What about this 1/2? How do we get this to be 0, the middle one? Well, all we need is add a negative 1/2 to this. Well, where is the negative 1/2 going to come from? Well, it will come from multiplying the pivot row by negative 1/2 and adding it to the second row. Let's write that down. Row 2, which is the row we're changing because 1/2, this positive 1/2 is in row 2. Row 2 is equal to minus 1/2 times the bottom row, row 3, which is the pivot row, minus 1/2 row 3 plus row 2 plus 1/2, or row 2. Okay, so these are the two operations necessary for us to get the reduced row echelon form. I would encourage you strongly to please pause the video, carry out those two row operations, and then come back to the video. Okay, all right, I'm assuming that you've done that. And now let me write down my solution. So I'm going to carry out this row operation first, this one. So this is saying multiply the third row by 1/2 and add it to the first row. So 1/2 times 0 is 0, plus 1, 1. 1/2 times 0 is 0, plus 0, 0. 1/2 times 1, positive 1/2, plus negative 1/2, 0. 1/2 times negative 1, negative 1 over 2. Negative 1 over 2 plus 5 over 2, that's 4 over 2, positive 4 over 2, which is 2. Okay, that's that. Now let's carry out the second row operation, which changes row 2. So this one says multiply row 3 by negative 1/2 and then add the result to row 2. So let's do that. Minus 1/2 times 0 is 0, plus 0, 0. Minus 1/2 times 0 is 0, plus 1, 1. Minus 1/2 times 1 is minus 1/2, plus positive 1/2, 0. Then minus 1/2 times minus 1, it's positive 1 over 2. Plus 5 over 2, that's 6 over 2. 6 over 2 is 3. Okay? And of course, then we can rewrite the pivot row as it was, 0, 0, 1, negative 1. Okay, so now compare this result with this. Are we done? We needed 1, 0, 0 in the first column. Do we have that? 1, 0, 0. In the second column, we needed 0, 1, 0. Do we have that? 0, 1, 0. In the third column, we needed 0, 0, 1. Do we have that? 0, 0, 1. Yes, we are done. So the solution of the system is the right-hand side column. Remember, the first column are the coefficients of variable x. The second column are the coefficients of variable y. And the third column are the coefficients of variable z. So 1 times x is x equals 2. 1 times y is y equals 3. 1 times z is z equals negative 1. So let's put the answer in proper form, which is 2, parenthesis, 2, comma, 3, comma, negative 1. Here's the final solution of the original system. Okay? I hope this is making sense. All right. So in this word problem, let's see what they ask us to solve. Remember, right from the outset, we haven't even read this word problem. But what do we know? We know that there's going to be unknowns and there's going to be known quantities. What are we going to do with the unknowns? With the unknowns, we must introduce our own variables for those unknowns. And then we're going to solve for those unknowns, okay? So that introducing your own variables, please don't forget that. All right, so let's read on. It says the top 3 apple growers in the world, China, the United States, and Turkey, grew a total of about 74 billion pounds of apples in a recent year. Okay? China produced 44 billion pounds more than the combined production of the United States and Turkey. The United States produced twice as many pounds of apples as Turkey. Find the number of pounds. Aha. See? That's what they want us to find. Find the number of pounds of apples produced by each country. Okay? Let's assign variable to that which they want us to find. So, the number of pounds of apples produced by each country. All right, for China, I will assign the variable C to the number of pounds of apples produced by China. Okay? So, for Turkey, let's assign the variable T. That would be the number of pounds of apples produced by Turkey. So I should have actually written down billions of pounds of apple, right? Because that's the unit the problem is using. So if you don't mind, let me use my thick marker here to correct that. So instead of, that's number of pounds, but we want to use the units that the problem is using. So we say billions billions of pounds of apples produced by China, billions of pounds of apples produced by Turkey, and of course, for the United States, let's use U as the variable. Billions of pounds of apples produced by the United States. Okay. All right. Now that we have these three variables, which reflect what we're looking for, let's set up the information. Let's set up the equations we need, right? We're using these variables. Without introducing these variables, we could not do it. So the top three apple growers in the world, China, United States, and Turkey, grew a total of 74 billion pounds of apples in a recent year. Okay, so that translate this first sentence into an equation. Can you please? Before I do it, please you do it. Pause the video, write down, using these variables, translate that first sentence into an equation. Okay, I'm assuming you've done that, and now you're back. So we can write C plus T plus U is equal to 74 billion, and the units are in billion. Okay, 74 billion. So that's the translation of that equation into that statement into this equation using the variables that we introduced. If you prefer, you can use X, Y, Z, but I use these variables because it helps me keep track of what's what as I go through the solution. Okay, so let's read on. China produced 44 billion pounds more than the combined production of the United States and Turkey. So go ahead and translate. So pause the video, please, and read this sentence and translate that sentence into another equation. Okay? Pause the video and do that, and then come back. All right, I'm assuming that you've done that. So let me now write this. China produced 44 billion pounds more than the combined production of the United States and Turkey. So that means if we combined production of Turkey plus the United States, that would be equal to China produced, I should have written that on this side, but it's okay. Let's see. So I'll put that on this side. So China, let me put that here, produced 44 billion pounds more than the combined production of the United States and Turkey. So that production of the Turkey plus United States plus, not equal to, plus 44 billion. Plus 44. Okay? That's the translation of that sentence. China produced 44 billion more than the combined production of the United States and Turkey. Okay, so that's the translation of that. Notice we can do all this because we introduced the variables already, right? That's the point. All right, that's the point of introducing the variables from the get-go. But you need to connect these variables to what you're looking for. Okay? So you need to be able to define them. As you introduce them, you need to be able to define them, as we did. All right. Then they say the United States produced twice as many pounds of apples as Turkey. So go ahead, pause the video, and translate that piece, that last, not last sentence, but the next to the last sentence, that one. Okay, go ahead, pause the video, write down the equation for that. Okay, I'm assuming you've done that, and now you're back. So the United States equals to twice as many apples as Turkey. So twice Turkey. Okay. All right. So notice what has happened. Now that we've reached the end of this problem statement, we have 3 equations and 3 unknowns, and that's a good match. Okay? So now we can solve this problem. We know we can solve it. We have 3 unknowns and 3 equations. All right. So this is our system. We can use either the Gauss-Jordan method or the method of elimination and substitution, either one. I think in this particular case, using the method of elimination and substitution to 3 equations, 3 unknowns would be easier. So that's what I'm going to use. Notice that in this bottom equation, we already have one variable given in terms of the other variable, right? So we can look back at these 2 equations above and replace the United States variable with this equivalent of it, with 2t. Let's do that. So in the top 2 equations, so replace the variable u in the top 2 equations with 2t. Okay? That's using that. Using that bottom equation, we can do that. Okay? Let's do that then. So we have, what do we end up with then? Essentially, we end up with a reduced set of equations. 2 equations, 2 unknowns, which is what we need before we can apply the method of elimination and substitution. Remember, that's how we started applying the method of elimination and substitution to the beginning examples that we had in this video. We're doing exactly that. So in the top equation, we have c plus t plus, when I get to u, I'm going to replace the u variable with 2t, equals 74. In the second equation, once again, c equals t. Instead of u, the variable u, let's substitute for it with 2t, then plus 44, right? So let's clean this up a little bit. So we have c plus t plus 2t. That will be c plus 3t equals 74, right? Then we have c equals 3t plus 44. So we know that we want all the variables on the left, right? So let's move this 3t to the left and keep 44 on that side. Like that. So now we can eliminate one of these. We can basically apply the method of elimination and substitution. But do we need to multiply anything, any equation by anything to eliminate any of these terms? Not in this case. Because as you notice, the t terms already have coefficients that are equal but have opposite algebraic signs. So you can easily add these two equations right away. So the t terms drop out. We end up with c plus c. It's 2c, right? Equals 74 plus 44. We end up with 7 plus 4, 11, 118. Okay, so now let's solve for C. So C, that's the billions of tons of apples produced by China, right? So let's calculate that. I suppose it's 59, right? It should be 59, but let me make sure. So 118 divided by 2, 59. Okay. So C is equal to 59. So that's the billions of tons of apples produced by China. What about the billions of apples produced by United States and Turkey? Let's find that out. Well, we know that the United States, well, let's plug this into this equation, any of these two equations. It doesn't matter which one. I'll pick the bottom one. So using, let me move this up a little bit over. Using this equation, using C minus 3t equals 44, right? Let's plug in for C with 59. We have 59 minus 3t equals 44. So let's solve for t here. We have minus 3t equals 44. Move the 59 to the other side. It was positive on this side. When you move it, it becomes negative 59. So we have minus 3t equals minus 15, right? And Turkey is negative 15 divided by negative 3, that's positive 5. So Turkey produced, in that same year, produced 5 billion tons of apples. And we know that the United States, according to this relationship, produced twice as much as Turkey, right? Let's make use of that. So using U equals 2t, then we have United States equals 2 times that, 5, or United States equals 10. So United States in the same year produced 10 billion tons of apples. Okay? So there we have it. The apple production for those 3 countries in a given year. Okay, so we've come to the conclusion of another section, and I'm very thankful to you for watching these videos and bringing me your questions. You're doing great. If you've taken my advice throughout this series of videos, you should be doing great. And so I thank you for sticking to this. And then for now, have a nice day, and I'll see you again next time.